Welcome to Study Loop.
In this problem, on the topic of thermal properties of matter, we are given the molar mass of oxygen, or the O2 molecule, as 32 grams per mole, and we are asked to calculate various quantities regarding oxygen. The first of which is the average translational kinetic energy of an oxygen molecule at a given temperature of 300 Kelvin. So to find this translational kinetic energy, we know this is a half times the mass of this molecule m times the average velocity squared. And remember, we can write this as 3/2 times the Boltzmann's constant K times the temperature of the molecule T. So we can write this again as 3/2 times 1.38 times 10 to the minus 23, which is in joule per molecule Kelvin, multiplied by the temperature, which is given as 300 Kelvin. This gives us the average translational kinetic energy for the oxygen molecule to be 6.21 times 10 to the minus 21 joules. So with the average translational velocity of the oxygen molecule, we can calculate its average kinetic energy. Next, for part B, we want to calculate the average value of the square of its speed. So to get this, we first need to find the mass of one molecule. The mass of one molecule of the oxygen is its molar mass divided by Avogadro's number, n, or Na. This is equal to the given molar mass, which is 32 times 10 to the minus 3, so that we can use the unit kilogram per mole, which is SI units, divided by Avogadro's number, which is 6.022 times 10 to the power 23 molecules in every mole. So calculating, we get the mass of the oxygen O2 molecule to be 5.314 times 10 to the minus 26 kilograms. So every molecule of this O2 measures 5.314 times 10 to the minus 6 kilograms. Now that we have the mass, and we also know from part A what the kinetic energy is, we said a half m v squared was 6.21 times 10 to the minus 21 joules. So from here we can find, as the question asks, for the square of the speed, so v squared, we can solve for v squared to be, if we rearrange this equation, 2 into 6.21 times 10 to the minus 21 joules over m. And we've just calculated the mass. So this is 2 into 6.21 times 10 to the minus 21 joules divided by the mass of the O2 molecule, which is 5.314 times 10 to the minus 26 kg. So we get the square of the speed to be 2.34 times 10 to the power 5, and this is meter squared per second squared. And so that's the answer for the square of the speed, or the average speed of the oxygen molecule. Now for part C, we are asked to calculate the root mean square speed of this molecule. Now, the root mean square speed is VRMS, and we know this to be the square root of V squared RMS. So the root mean square is simply the square root of the square of the quantity, which is the square root of V squared, which we calculated previously as 2.34 times 10 to the power 4 not 10 to the power 4, but rather 10 to the power 5, as we calculated above, in SI units of meter squared per second squared. And calculating, we get the root mean square velocity, VRMS, of the oxygen molecule to be 484 meters per second. So that's the solution. We have the root mean square velocity, the root mean square speed of this molecule. Now in part D, we are asked to calculate the momentum of an oxygen molecule that is traveling at this speed. Now we have the speed, we are asked to calculate the momentum. We know the momentum P is equal to the mass of the molecule M times the RMS speed, so VRMS. Now, the mass of this molecule we calculated earlier to be 5.314 times 10 to the minus 26 kg times VRMS of 484 meters per second we calculated in part C, and we get the momentum of the molecule traveling at this speed to be 2.57 times 10 to the minus 23 kilogram meter per second. And that's the momentum of this molecule. Now we go on to part E of the problem, which asks us to find or says that if we suppose that an oxygen molecule is traveling at this speed and bounces back and forth between opposite sides of a cubical vessel with a given side length, we want to know the average force that the molecule will exert on one of the walls of the container. Okay, so we know the time between collisions with one wall, we'll call T, is equal to the distance 0.2 meters divided by the speed at which the molecule is traveling, which is VRMS, which is 0.2 meters divided by 484 meters per second. And we get the time between collisions to be 4.13 times 10 to the minus 4 seconds. So that's the time between collisions with one wall. In a collision, the speed, or the velocity rather, changes direction. So the change in momentum, delta P, is equal to 2mv RMS. And that's 2 times the momentum calculated above, which is 2.57 times 10 to the minus 23 kg meter per second. So this gives us the change in momentum of 5.14 times 10 to the minus 23 kg meter per second. So now that we have the change in momentum, we can calculate the force that is exerted on the wall. So F, we know, is the change in momentum, delta P, in the change in time. Or we can use an infinitesimal, dp dt. So force is defined as the rate of change of momentum, dp dt. And so the average force is delta P by delta T. So some finite change in the momentum over some finite time, which is 5.14 times 10 to the minus 23 kg meter per second in a time of 4.13 times 10 to the minus 4 seconds. And so calculating, we get this force, this average force, to be 1.24 times 10 to the minus 19 newtons. So that's the average force that this molecule will exert on one of the walls of the container that it's contained in. And that's the answer to part E. Now for part F, we had asked for this average force per unit area, which is essentially the pressure. So the pressure we'll use the word pressure since we use P for momentum. And we know pressure is simply the force per unit area, so F divided by A. And that's a force of 1.24 times 10 to the minus 19 newtons over the area of this container, 0.1 meters all squared. And so if we calculate, we get the pressure due to a single oxygen molecule to be 1.24 times 10 to the minus 17, and this is SI units, which is pascals. So that's the pressure of one oxygen molecule that is exerted on the walls of this container. Next, for part G of this problem, we want to know how many oxygen molecules that are traveling at this speed are required to produce an average pressure of 1 atmosphere. So we know the pressure now is equal to 1 atmosphere. And 1 atmosphere in pascals is 1.013 times 10 to the power 5 pascals. So the number of molecules needed, we'll call N, is equal to 1.013 times 10 to the power 5, the total pressure divided by the pressure exerted by one molecule, which is 1.24 times 10 to the power minus 17, which we calculated above, and that's pascals for every molecule of O2. And so calculating, we get the number of molecules required that are traveling at this speed to give us a pressure of 1 atmosphere to be 8.17 times 10 to the power 21 molecules. So that's the answer for part G of the problem. And lastly, in part H, we are asked to compute the number of oxygen molecules that are contained in a vessel of this size at a given temperature and atmospheric pressure. And we said that the answer for part H should be 3 times as large as the answer for part G. And if it isn't, we want to know where the discrepancy arises. So we know that from the ideal gas law, PV is equal to NKT. So N is equal to PV over KT by rearranging this equation. And again, all of these values are known, so we can put them in. The pressure is 1 atmosphere, or 1.013 times 10 to the 5 pascals, multiplied by the volume of this container, which is 0.1 meter all cubed, divided by Boltzmann's constant, which is 1.381 times 10 to the minus 23 joules per molecule Kelvin, multiplied by the temperature of 300 Kelvin. And so calculating, we get the answer to be 2.45 times 10 to the 22 molecules. And if we look at this solution, we can see that it's not the same solution that we received in part G. And so we want to know why this discrepancy arises. Now, this discrepancy arises from the factor of 1/3 in the following equation. So in one direction, we have the velocity, the average velocity, v along the x direction squared is simply 1/3 of the total square of the average velocity.